Our Implementing Routing Facilities for Mobile Workers ELT lesson offered the opportunity to create and deploy an implementation plan for mobile workers connectivity under several related scenarios. In this lesson, we will review our demonstration and try to reach some conclusions. Let's debrief. Our demonstration provided a quick overview of mobile worker connectivity from the perspective of routing facilities. The functionality we implemented in this demonstration is shown in our right panel. It includes IPsec VPN verification, routing of VPN address pools, and NAT. Look at the successful ping command at the remote connecting client. It is reaching the loopback interface on R2. Let's take a look. Here our VPN client connected, and we can quickly ping the remote loopback and see that it's successful. As we return to our three-way panel, that's the scenario we're obtaining. We are establishing the VPN and are able to ping remote destinations. That means that not only are the address pools working, but also that EIGRP is advertising the address pools for the remote clients. So there is end-to-end reachability to and from remote, non-directly connected networks. Remember, we use the show crypto ISACAMP SA command to verify the tunnel was active. Even though we're not going into detail as to how the command works, we are giving you the commands to verify things are working, and the configuration is there. We also used the show crypto engine connections active command to display packet counters and demonstrate that encrypted and decrypted traffic is going through. Our configuration was more task-oriented. Remember, our first major task was to allow IPsec in our firewall. That includes the 4 protocols and ports necessary for IPsec, including ESP, AH, ISACAMP, and NAT traversal. For our demonstration, it was not so important to know what each of these does, as much as it was to know that they exist and to be able to identify them with protocol numbers or port numbers in our access list. Look at the access list here. It is, in fact, allowing the IPsec traffic. Look at the matches of traffic hitting each line of the ACL. In terms of address pools, we did not go through the complete configuration as to how they are assigned to the IPsec configuration. But we did see how the VPN software client was able to obtain an address in the pool as soon as the VPN was established. Routing presented several options, the most dynamic one being the IPsec function called reverse route injection. Our configuration followed a more static but less complex approach of using a static route and redistributing it in the EIGRP domain. Here's our static route, pointing to the address pool belonging to the remote access clients. The address pool can be displayed with this command called EasyVPN, and there's our range. The range is being advertised to EIGRP via this static route. In terms of alternative configurations, the list here summarizes our options in terms of routing services around the VPN. We discussed the advantages and disadvantages of each, and our conclusion was that RRI, reverse route injection, was the most suitable and dynamic solution. Other solutions include the use of an existing subnet, which requires proxy ARP on the VPN router, the use of a new subnet, which involves the use of similar solutions to the ones we used, which was static routes, and RRI, reverse route injection, which will insert the VPN client route automatically into the routing table. You can then redistribute it into your dynamic routing protocols. In fact, we can test it now. If I go in and remove the IP route, the static route, we should have no connectivity from the client into R2. Without looking at the details too much, the configuration of reverse route injection goes like this. It's very simple. I've disconnected the remote VPN client. We can verify the entry in the routing table is not there. Let's connect the VPN client and see how the entry appears in the routing table. I'll go out to the VPN client, connect it, verify that it is connected, and that it obtained an IP address in our pool, then go back to the router and verify a static entry has been automatically added. If I disconnect the client, it will go away, which is why this is a dynamic option. Notice one of the drawbacks here. The entries are added with a /32 mask. If you have several hundred clients, you will have the same number of entries in the routing table when they are all connected. What else did we learn? Well, with a handful of commands, we learned to identify the existence of IPsec VPN configurations and monitor their health in Cisco IOS routers. Our configuration of those verification commands was not thorough, and it was not detailed, but those commands will prove useful as we move forward and learn more about VPN configuration and maintenance. In terms of routing, we learned that usually the simplest solution is the more suitable for most environments. Reverse route injection is the most dynamic and advanced solution to the routing issue. But we were able to successfully route traffic back to the VPN clients with a simple static route and redistribution. The classical considerations of using static routes still apply. They are static. So if the clients are disconnected, the entries are still there and still being advertised to the rest of the network. One important issue is the NAT bypass issue. VPN traffic does not need to be subject to NAT. In its purest form, before that traffic enters the VPN tunnel, it is considered private internal traffic, going from one internal area of the network to another. The fact that it does so by using a public network is not irrelevant, but should be transparent to both endpoints. The figure illustrates the point. The public addressing will be given by both ends of the tunnel. But we start with a private packet that uses private addressing. The packet is encapsulated into a larger packet as it traverses the public network. The larger packet will have public addressing. That's why we should not apply NAT to the private addresses. They remain private all the time inside the tunnel and encapsulated. As soon as the packet gets to the other side, it will be decapsulated and private addressing remains. Looking ahead, the next scenario you may encounter is probably going to be configuring the IPsec VPN itself. This requires knowledge of the protocol and its operations, including the use of remote route injection for routing purposes. Most likely you move on to configure more services around the VPN, including firewalling to protect the network, and perhaps security policies, such as intrusion prevention systems or network admission control, or perhaps quality of service, to maintain consistency of traffic priorities across the tunnel. User authentication and identity management are also important, especially if you are allowing hundreds or thousands of users to engage in remote access activity and connectivity. AAA services, authentication, authorization, and accounting, are your next step in that area. Finally, SSL VPNs are becoming more and more the option of choice for remote access connectivity, so you will probably be looking into this as your training progresses. This is the end of our module. Let's move on to another topic.